Hello, today we'll talk about graphs and how to implement them in Scala programming language. We'll touch upon just basic functions on the graphs, adding nodes, vertices, and doing a breadth first search, and a little bit about pathfinding as well. First, what is a graph? So graph is a concept used often in math. There's a whole graph theory around them. But essentially what it is, it's a way to represent an information. So we may have vertices, so you can think about them as nodes, and we may have edges, so you can think about them as links between those vertices. All right? And the actual representation of what are they representing, it really depends on the context. So for example, we could have cities. So we could have cities of Riga. We could have let's say it's a New York City, city of New York City, NYC, right? We could have the Washington, D.C. We could have the Los Angeles, and we could have Vancouver City, right? And we may have the airline traffic routes from Riga. There's a way to get to New York City. There's a way to get to the Washington, D.C. There is a way to fly between those two cities. We can certainly fly to LA from New York City and Washington, D.C. And from LA, we can fly to Vancouver, right? So what is the best route? Sometimes graphs may have weights on the edges. So those are called the weighted graphs. So we may consider that this route is 8 hours, maybe this flight is 9 hours. This flight might be 7 hours, so this might be 6 hours. I'm just making up these numbers. And this might be, let's say, a couple hours, just 2 hours or so. Now the question is, which is the fastest route? So, and of course, here between DC and New York City, this may take less than 1 hour. So we may have a few options here, right? So one option might be, let's take the shortest route from Riga, or the fastest route to New York City, which is only 8 hours versus 9. And then from here, we can take the shortest here to LA, and then we get to EC. All right? How do we write a program that actually finds that path? How do we write a program that encodes these paths, these cities as vertices in the graph, or a general graph? That's what we're going to find out, and we're going to do it by doing live coding. I'm going to open IntelliJ IDEA. I have created an empty project. I called it graphs. I'm going to have a Scala class, an object, all right? I'm going to call it the test, okay? Test main. Okay, so this is going to be the object that creates the graphs and that tests it all right? So that's my object here. I'm going to create another Scala class, which is going to implement the graph. Okay, I'm going to call it graph. It's going to be a class, all right? So now we have two source files, test and graph, to create our code. So sometimes when I code something new, then before jumping into the implementation of the actual data structure or something, I'm thinking out loud, how am I going to use it? What are the functions going to be that we will need to actually do something with that object, with that class, right? So I'm going to do that here. Let me create the main function, and as part of the main function, one thing is for sure, we are going to create, let's say, a graph. Let me call it G. And the type of it is going to be graph, new graph. And that's it. So we have created the graph. Now that I have created that graph, I may want to add the cities and I may want to add the routes between them. The way to do it would be called g.addVertex, which is going to be a city, right? Let's say I'm going to add the name for the vertex, okay? The name for the city. Apparently, we're going to need that function addVertex, okay? We may create different graphs. For some graphs, the vertices will represent cities with the names. For some graphs, the vertices may represent different kind of data. It may represent numbers, integers, maybe floats, maybe a complex data structure. So therefore, I'm going to define another parameter when creating a graph class. It's going to be the type of the vertex. In my case, it's a string. Remember, this is just the usage of the class, right? We're going to have to define that class in a moment. So maybe we can jump to the graph and actually implement the add vertex function. Remember, we had to define a type. So let's do it here as well, right? So graph will have a type. I'm going to call it v because it's the type of the vertex. All right, and let's see, what do we need for that? We need some place where to store information about vertices, right? So therefore, I'm going to have vertices. That's going to be one data member, all right? So that's going to be, let's say, let me call it a variable for now. Maybe it's going to be enough to have a value, but we'll see. And when we create vertices, the vertices actually are going to be these nodes, these cities in our case. So we could store them in a list, right? So let me do that. Let me create a list. And this list is also needs a type. So that type is going to be v for vertices, right? And let's initialize it to an empty list. All right, so when we create it, there is no vertex in it. Similarly, what else do we have? We have the edges. We actually have these routes between the vertices, right? So I'm going to have edges, variable edges, all right? And what's the type for the edges is going to be? So we're thinking about the implementation of the graph, which is a class, right? And of type v. So we decided that we're going to have vertices, all right? And the vertices are going to be of type list of the same type v, right? But we also need edges. And the edges may be represented if vertices is, it's like a list of, or it could be an array or a collection or something. So essentially it stores the names of the cities, right? So that's the vertices. So for the edges, I may also want to look up these cities. And for each city, I may want to look up what routes are there that links this city to other cities. So it could be that every city, so this is going to be the list of cities, will have another list of vertices, right? So if I have, let's see, Riga, New York, DC, LA, and VC, so let me redraw a simple representation of that map. So there we have R, right? So these are the links between these cities. Then I may have an entry for Riga. So this is going to be Riga. So we have Riga, we have New York, DC, LA, and Vancouver. And Riga has two links. It has a link to New York, and it has a link to DC. The next one is New York, and New York also may have links to Riga, as we discovered already. It has another link to DC. It also has a link to LA, Los Angeles. DC similarly has a link to Riga. It has a link to New York. It has a link to Los Angeles as well. LA has a link to New York. It has a link to DC, and it has a link to Vancouver. Okay? And finally, Vancouver has a link to LA. And that's it. All right? So this is how we could represent our graph in the memory. This is a list. And this has keys and values, right? So this whole thing together is a map, right? And the values of the map are actually lists, right? So these are lists. Now this list is of type V, vertex, and these lists are also going to have the type of V, right? So the map actually is the keys are going to be V's, so the map is going to have the type of V, and it's apparently going to be mapping to a list of V's. So list of V's, right? So this is the blueprint for the data, for the storage of the data, representing a graph. And now we need to implement that in the code. So let's do it. We just decided that we have the vertices as list already. So the edges are going to be a map. They are going to point from vertices to list of vertices. All right. And of course, we need to start out with an empty map. Okay. So we're good so far, I think. We have the data to represent the whole graph. Do we need to represent anything else? I don't think so. I think that all the information from this picture is captured in our data. At least we are capable of capturing all the information. So in order to do that, we need some functions. We need to define a function add vertex. And when we add the vertex, we actually need to add the name of the city for our example. So let me call it a value. And the type of this value is going to be V, right? In the context of the cities of the map, the value is actually going to be the name of the city. And the type V is going to be a string, right? And what is this going to return? So for now, let's say it returns a unit. Nothing, right? So now that we have this defined, then we can think of how should we place that information, this new value, this new string that comes from the city. We need to register it with vertices, obviously, right? So therefore, we need to write vertices are equal to the new value added to vertices, right? So we basically take all the vertices, the list of all the vertices, we use the concatenation operation, and we add another node to that list, and that creates a new list that is added to the vertices. That actually is assigned to the vertices, okay? So we are done with adding vertices. Do we need to do anything else at this point for the graph? Well, seems like we don't have to do anything because we don't have any edges at this point. But the thing is, we will have edges soon enough. So we need to register a new entry in this map for the edges that points to a list that initially is an empty list, so that we have space where we could add those edges later on, right? So let's do that as well. And let's say edges plus equals will add a new entry to the map. And the way we add entries to the map, we provide the key and the value that are separated by this arrow thingy. Okay, so the keys are our value, all right, and the actual value is going to be a list. It's going to be an empty list, and the type of that list is going to be determined by the way the edges are defined. So therefore, it's going to be the list of vertices. All right. Okay, so now that we have add vertex, we have the test main. All of a sudden, this is not red anymore. So we can certainly add value to Riga. Okay, so perhaps we can add a few more cities this way. So we have New York, we have Washington, D.C., we have Los Angeles, and we also have Vancouver. All right. So we have defined all the vertices. What comes next is we need to add edges. But before that, one good practice is to test out your code as you write it, rather than write the whole code and test it at the end. Because there might be small problems or mistakes that we have created that it's good to catch them earlier. So therefore, I'm just gonna take and build the project, right? And it's trying to be compiled, and it tells me it has built it successfully. Okay, good. So apparently we have good code. Hopefully it does what we are intending to do. What we could do, we could add actually, in order to test, we could add another function, which is not a classic function for graphs, but which will help us to debug these things. Okay, so I'm going to add a function that's called print, that will print the information about the graph. Okay, and it will return nothing. So return type is unit. So when we print the information about the graph, I think we will want to print the vertices, and we will want to print the edges. Okay, so therefore print line is what we're going to use. The first thing is going to be vertices. Okay, and then after a while we are also going to print the edges. All right. And I'm just gonna print done at the end so that I know where the list of the edges ends. We don't have the edges yet, but we do have the vertices. Okay, so let's have a loop that loops through all the elements of that list, okay, and prints those vertices. Right? How do we write a loop? We could use a for loop. All right, and we could go for, let's say, v from vertices. What do? We just want to print them. Print line v. Okay, and then I hope that v actually has a function defined that converts it to a string, which will be called in order to print it symbolically. Okay, but if you want to be more explicit, you could type toString here, and then you would explicitly ask this to be converted to a string, because we don't really know what the type of that vertex is going to be. In our example, it is a string, it is the name of the city, but it might be different for different kind of applications. All right, so we have that. Let's test it. All right, so now we should be able to actually call gprint. Okay, and let me compile it. So another way to compile it is to press Control F9, which I'm going to use further on. And now that we have compiled it, I want to run test main. Let me run it. And there you go. Our project has been compiled. We have run it. The cities, the names of the cities have been printed. The edges are not there yet, but we are getting there. All right, cool. So we have the edge, the vertices. Let's get to the edges. All right. Do we have edges? Yes, we have edges in this picture, but we need to encode them in the code, right? How could we add them? What would be a convenient function to add them? So we could call g.add edge, and then we need some parameters. Okay, so one way to add them might be by the names of the actual cities. So we could add edge between Riga and New York, right? But then what if we make a typo somewhere, and it's kind of asking for a mistake, for a bug, for a disaster, if we want to repeat the same names again and again and again. What if the name of the city changes? What if we decide that we are not going to talk about NY, but NYC, for example, right? New York City. Then we would have to go through all the code and change that. So therefore, the way I'm going to do it, I'm going to assign these vertices I will ask for this add vertex to actually to return a vertex that it has created. All right. So I'm going to have value Riga. Okay, or I could just call it R and assign Riga to it. All right. Now the problem is though that this function does not return anything yet. Okay, so let's do it. Let's say that it returns the same vertex and let it return the value. All right. In a more complicated example, you may have a more complicated data structure for a vertex, which stores the value and perhaps some other information about the vertex, some, I don't know, weight on the vertex, for example. So then we would return the reference to that vertex itself, the newly created vertex. In our example, we keep it simple for now. So we return the same value that we got as a parameter after it's been added to the vertices and after the new empty list for the edges has been created for the vertex. Another thing is, note that I'm not checking here for values that have been added already to the graph, right? So there should be more error checking perhaps, or at least we should talk about whether we are distinguishing between vertices that have the same name or not. So that would need a bit more implementation. But for now, let's assume that as a tidy programmer, I am not going to add vertices with the same name, right? So now it looks good. The only thing is that I want to add vertices, the variables for vertices here as well. So N is going to be for New York City, DC is going to have N, no DC, LA is going to have L, and VC is going to have V. Which is kind of the vertex stands for V, so that might be confusing, right? So maybe let's be nice and let's type it out completely. It's going to help us out in the long run. LA is going to create less confusion, all right? So now that we have these values, we can use them as references to the vertices that we want to create edges for. What's the first edge that we should create? Between Riga and New York City, okay? So let's do that. So Riga, New York City, New York. And voila. So that should be enough to create that edge. But it's in red, so it's not implemented. So let's go back to the graph class and let's implement that edge, all right? So we had the add vertex function. Let's define add edge function as well. So remember that we decided to use vertices, meaning the same type V, when adding edges, right? So the same type V from here that we return, we can use to add edges. So therefore the types are going to be V1, not the types, but the actual name for the parameter, and the type is going to be V. And then the second edge is going to have V as well. All right. So now that we have this edge represented by vertices, we can actually try to add it. I'm going to return unit, meaning nothing important. And how do we add this edge between two vertices? Let's look at the picture once again. So when we have another edge, we need to add it by adding it to the list of the first vertex with the name of the second vertex. But we also need to do it for the second vertex with the name for the first vertex, so that we can find the way in one direction and then the way back as well, right? Note that there is another kind of graphs, which is called the directed graphs, that actually have edges with directions. So it might be that you can fly from Riga to New York, but from New York to Riga you cannot, or perhaps there's a different cost for flying from New York to Riga, which is how it is actually. When you fly across the Atlantic Ocean, it may take 1 hour longer if you go one direction versus the other direction, if you go west versus east, due to the way the Earth is rotating and the big masses of air are moving. So, but in our case, we still keep it simple. We're going to have generic edges with no direction. So therefore, we need to add to the list of one vertex and then to the list of the other vertex. We need to register them. So how do we do that? We need to add to the list of the list that's registered with edges. So therefore, we need to get that list from Riga. We need to get that list. How do we get that? We take edges, and we take one vertex. We find all the edges for the one vertex, right? And then we add, so this is a list of vertices, right? So therefore, we need to add to this list just like we do with lists, with immutable lists anyway, like so. So we have added, now we have created a list that has v2 appended to the original list of all vertices, all edges registered with v1, right? But of course, we need to update the list for v1 like so. Okay? And then we would also have to do the same for v2. So we need to get the list for v2 and add v1 to that list and update the list of edges for v2, right? So I'm going to just copy this line and change v1s to v2s and v2s to v1s, right? All right, so seems like we have some code, and perhaps it is time to test out whether it's going to compile or not. All right, we have one edge to be added, so we are calling that function, so that's fine. We have the function implemented here, right? Let's see if it works. Okay, so I'm going to compile it first, right? Let me try it. So I just pressed Ctrl F9 and we have an error. So what is the error here? Where do we have error? We have error on this line, and this newly created line. And it says that value update is not a member of map. So what does that mean exactly? And the problem is that map, just like list, is immutable data structure, meaning that when you create it, you cannot change it, right? You cannot update the value. And what we tried here, we tried to update the value for a list that's registered in the map for the v1 vertex. How do you solve a problem like that? And one way is just bite the bullet and go for the mutable data structures. So let's go for the mutable map. So turns out Scala has a library, built-in library, a collection that has all kinds of data structures that are mutable, that we can actually change the values for, right? It might not be as efficient. One reason for keeping immutable data structures is that if we really intend the value of the data to be immutable, then we can be sure that anyone else who tries to change our code later and tries to add something to it or to that value or change that value is not going to be able to do it. It's going to be warned early on by the error message from the compiler, right? So that's one reason why immutable data structures have been introduced, right? In our case, we do need a mutable map though. So therefore, I'm going to change the type of this map to mutable, right? And I can do it like so, right? And for some reason, it's not recognized. And the reason it's not recognized is because we need to import that library that actually has mutable data structures, right? So when I created this context action, import the library, it added this line. So it imported that Scala collection mutable. And now that we have that, we can actually use mutable map. But the thing is, so let's try to compile it before jumping ahead. Let me try to rebuild it once again and see if we have solved the problem. And turns out, no, we have not, right? And the problem is that now the problem is in this line because we have one type for the edges, but we are trying to create an immutable map and assign it to the edges. That's not good. So if we are dealing with mutable maps, then we need to deal with mutable maps here as well. All right, let me try to compile it now. And now it says everything is cool. We have the green check mark, the code compiled. Okay, so that's good news. We could add the print function so that we could actually see the edges that we have added. So let's iterate over edges, all right, for our print function. And let's just print them, okay? So I copied the loop from vertices. So I'm gonna create loop for edges. And let's print the edge. And let's see how it works, okay? So we have added one edge. We could try to run it and see what happens, all right? So let me run it. We could also run it by clicking on this green triangle. So it prints all the vertices here, which is exactly what I expected. Well, except they are in the reverse order from the way we assigned them, which is fine with me, but what can you do? They're still there. And then there's this list of edges. And each edge, LA has an empty list. Riga has a list with one element, New York. That's because we added link from Riga to New York. New York has one element, Riga, because we added that edge, right? So remember in the code here, we had to add edge for both vertices so that we can find the way to the other vertex and the way back as well. All right? And VC has no edges, empty list, and DC has no edges, empty list. All right. So perhaps we can populate our graph further on the way we have in our example here. And let's add the missing edges from Riga to DC, from DC to New York, from DC and New York to LA, and to Vancouver. All right. So let me try that. Let me add a couple of these edges from Riga to DC. Now from DC to New York. From New York to LA. So I'm happy now actually that I decided to name those variables not just using one letter, but a full word. So it's much easier for me to remember them. So from DC to LA, and from LA to Vancouver. Okay, so now we should have the whole network added to our data structure. And let me see if it works, right? Let's run it. And what we see here is, well, the vertices have been printed. That's nothing new. And the list of edges are also printing nicely as expected, right? So New York, from New York, we can go to LA, DC, and Riga. From VC, we can only go to the LA. From the DC, we can go to LA, to New York, and Riga, and so on, right? Okay, so with this, we have implemented a very simple graph with vertices, with edges. We use list for vertices. We use the mutable map for edges. And we can create this graph, and we can do something with it. For example, we can print it.